The second half of the week 3 lecture is on variability, also referred to as dispersion or variation. And basically, variability provides a quantitative measure of the degree to which scores in a distribution are spread out or clustered around the mean. Measures of central tendency provide an indication of where the center of the distribution is. So if you recall, when we were looking at the central tendency, the measures of central tendency, the mean and the mode, they were centered right at the apex of the curve. So that's what I mean here when I say the center of the distribution. And measures of variability are how spread out the observations are around the center. Let's look at two distributions. The first distribution goes from 81 to 102. And we have a distribution that goes from 81 to 102. So the second distribution goes from 5 to 112. So it's more spread out. Let me just grab my pen and kind of take a look at, so that this distribution will kind of look like this, whereas this distribution will not be quite as spread out. Okay, it'll be more leptokurtic than platykurtic, if you recall those terms. So let's take the next slide. The measures of dispersion or variation are, and sorry about that, the measures of dispersion or variation are the minimum or lowest score, the maximum or highest score, the range, the lowest number to the highest number, and quartiles, which divides the whole distribution into 4 equal quarters, variance, which is the average spread of scores around the mean, and perhaps the most important of all, standard deviation, which is the square root of variance. It's the most widely used measure of dispersion there is. I'm just going to pop over to the other screen for a moment, and let's take a look here at standard deviation and variance. Remember that higher values, this is important, higher values for standard deviation and variance indicate more variability or spread around the mean. So it's going to be a more platykurtic curve, whereas lower values indicate observations that are more clustered around the mean, which gives us a more leptokurtic curve. The graphic representation of a population with a mean of mu equals 40 and a standard deviation, which is this symbol, is the small, right here, this is the small version. You know how we have a capital A and a small a in English? Well, in Greek, this is the capital sigma, and this little guy is the small sigma. So, and that means standard deviation. And here it would be equal to 4. So the mean is equal to 40 right here in the middle, and the standard deviation is equal to 4. Okay, and the sigma shows the distance from the mean. To compute the standard deviation, you need to compute things in this order. You need to compute the mean, the sum of squares, and the variance. Okay, and SS, or sum of squares, is the sum of the squared deviation scores. And don't worry about all these names. We'll get them in a minute. Variation, or variance, is the mean of the squared deviation scores, and the sum of squares is divided by the number of observations. Okay, so let's take a look. Computed standard deviation is the same and yet different for a population and a sample. For a population, don't forget the parameters are population size is a big N, and mean is mu, and sum of squares is SS. And if we look at that, the whole formula right here equals sigma x minus the mean squared. So we'll get into that in a minute. It's real easy to do. But in the meantime, the variance equals the sum of squares divided by n, or the number of observations, okay? And the standard deviation equals sigma equals the square root of the variance, all right? And if you look at the sample side of the house, we're seeing that it is a statistic, not a parameter, and it's a small n, and the mean is an x bar, or a large M, and the sum of squares is exactly the same, except we're changing the terminology. Instead of using an x minus mu squared, we're using x minus m squared. So it's the same numbers, literally, but just different symbology. And just to tell us that we're working on a sample rather than a population. And the variance is, this is where the difference comes in. This is where the mathematical difference comes in. It's the only thing that's really different. Instead of over here, we're dividing the sum of squares by n. Here we're dividing the sum of squares by n minus 1. All right? And everything else is the same, except that we're calling sigma s in a population. So standard deviation equals s, not sigma, in a population. It's still the square root of the variance. So here's my x bar sitting in the middle of the screen with the screen full of reminders. Population size is a big N, sample size is a little n, population mean, which this symbol here reads mu. Don't forget, when you can't remember it, it's kind of like a fancy M, okay? It's a mu. It's not a U, it's a mu. And sample mean is an X bar or an M. And population standard deviation is small sigma, and sample standard deviation is a small s. All right? So variance for population versus a sample. Population variance equals sigma squared equals the sum of squares, and divided by n, and you know what's coming next. Sample variance is the same number, it's just a different symbol. It's an s instead of a sigma, squared equals the sum of squares. Is it n? No, it's not n, it's n minus 1, and I'll explain that momentarily. So why n1 for the sample? This is why, to correct bias in sample variability. And what do I mean by that? It happens, sample variability happens because the spread of data around a mean is smaller in a sample than in a population. Why is that? Because we don't have as many observations in a sample as we do in a whole population. So it would make sense that it would be, the spread would be smaller. Dividing by n1 instead of n results in a larger number, thus correcting the bias and resulting in an unbiased estimate. Got it? Okay. I'm just about ready to change slides. After this slide, I'm going to do that. So remember, to compute the standard deviation, you first need to compute the mean. Secondly, you need to compute the sum of squares. Third, you need to compute the variance. All right, and we're going to now do an example, and I'm going to stop and go to the next, so I don't go over 15 minutes. I'm going to go over to the next video lecture.